Hello, welcome to the Repair Specialist, and this video is about explaining why and how a two-stroke engine can run in any position. So it can run vertical, horizontal and upside down. And as we know, other machines fitted with four-stroke engines can't actually do that because it would cause a lot of damage. And so in trying to show an understanding of how two-stroke engines and their carburetors work, I'm going to show the fascinating intricacies there that allow these engines to work in any direction, and that's the reason why they're used in small garden machinery such as strimmers, chainsaws, etc. that are used in all different positions. In fact, without the good old two-stroke, we wouldn't have machines out there with this level of manoeuvrability, especially at the price that they're available to us at. We might well be able to find a new engine more like a four-stroke that can work in all directions, but it will be at a different price, so we need to respect these little engines. Okay, so first of all we'll bring in a carburetor, and normally we get a little tiny carburetor like this on the two strokes. And in order to show my point here, we'll have to make this diagrammatically. There we go. And this is a side view of something like the carburetor we've just seen. And we'll move this carburetor over here, and then on this side here we'll add the engine. So in order to show you how the two-stroke engine with its carburetor can run in any position, upside down, to the side, etc., I need to just go through the workings of it to show you how that allows for that. First of all, we'll break it down and take a look at how the engine accomplishes this, and then we'll see how the carburetor fits in with that. So just to focus in on the engine then, we'll remove the carburetor and move the engine over here. So there's our two-stroke engine, but what I want to do as well is put a four-stroke engine here next to it so that I can show why and how these two-stroke engines can work upside down and why the four-stroke in comparison cannot. Okay, so let's take a look at the two. But without going into too much detail on how these engines work, because I've already got videos here on YouTube about how these engines compare with each other with function, I just want to go through the key differences as to why we can't use certain engines upside down and why we can use two strokes. First of all, let's take a look at why a four-stroke engine can't work on its side or upside down. And I know it may seem obvious to somebody who knows a little about engines why a four-stroke engine can't work to the side or upside down, but it all relates to the actual engine oil inside the sump here. And so why is that then? Why does this engine oil inside here stop this engine from being used in other positions? Well, let's turn one of these engines on its side and take a look. And of course, if we did turn one of these on its side, we'd notice there that the oil wouldn't actually be in this position, of course. It would be more like this. I realise I've put this diagram here to the extreme on the side there, really horizontal, but we certainly wouldn't need to get the engine in this extreme horizontal position in order to have problems here. In fact, in this position the engine probably wouldn't run at all. I'm just overemphasising this just for the sake of putting my information across. And so we've already established then that the engine oil there would be in this position, of course, because it's a fluid. And the trouble with that is that even before the engine started, the fluid will start to go up towards the piston and gradually seep up alongside of it, even though there's a very, very tight clearance there between the piston and the cylinder. And when the engine starts and the piston begins to lower, two main things happen. First of all, that lowering piston slaps into that oil that was sitting behind it, and that lowers the piston's speed and efficiency. And because there's such a concentrated amount of oil there in an unnatural place where it shouldn't be, then some of that oil, a small amount, manages to get past the piston there and seep past the piston rings and find itself at the top of the piston where it shouldn't be. And even though it's a small amount, it still causes problems, and we'll see that shortly. And as that slight speed reduced piston comes down even further to bottom dead centre, it experiences more of that oil behind it. And as it drives into it, it experiences even more resistance from it, because we've got an even greater mass now of oil as it gets down further. And so the situation now is that we've slowed the piston down even more because of that greater amount of oil. Plus, we've got oil there that's gathering even more than usual between the piston and the cylinder there, and that's creating like a drag on the piston. I just want to emphasise that the gap between the piston and the cylinder wouldn't be this large. I've had to emphasise it this much in order to get my point across. The clearance here, the gap, would be so small that it could hardly be seen. And so the piston now is moving far slower and less efficient than it would be than if the engine was sitting upright. Also, we've got more of that oil that's managed to seep past the piston rings there, and we'll see a problem with that in a moment. And so as that piston starts to rise again, we might think it will have free travel up the cylinder here, but we'd be wrong, because all of that oil that came past the piston ring, which is now sitting in front of the cylinder, is now causing a drag on the piston itself. It may only be a smaller drag, but it's still a drag. Also, we've got the drag from the oil in between the piston and the cylinder, which is also lowering the efficiency of this piston again. And when the piston gets to top dead center on the power stroke, where it should be compressing just air and fuel, we find now that it's compressing air and fuel, and it's also trying to compress all of that oil that got to the top of the piston, and that's causing problems now with combustion. Because when the spark plug fires, instead of it igniting that rich mixture of air and fuel, so that atomized fuel, in order for a great combustion in there to allow the piston to be pushed back down, instead it's trying to ignite the fuel and air as well as this oil, and this engine oil is nowhere near as ignitable. So the factors now reducing the efficiency of this piston are that it was already coming up to this point at a reduced rate, as we saw, because we've still got the drag there between the piston and the cylinder there, and now it's trying to compress this air and fuel with the oil in it, which is going to be harder to compress, so that'll slow the piston down even further. And now combustion's took place, the piston will be pushed back down that cylinder, and instead of travelling down the cylinder at a high rate as a result of a good combustion that's occurred, we've actually got a substandard combustion that's occurred because of the oil that was in there. So we didn't have the same explosion. So it's now travelling down that cylinder at a lower rate. And as if that wasn't enough, we've still got the oil drag this side of the piston as we did before, as the piston's lowering. And if we were to take a look above the piston now, in the wake of the combustion that's just occurred, we wouldn't have the usual exhaust fumes in there as a result. It'd actually look more like this. There would be so much more waste in there in the form of blue or black smoke as a result of that incomplete combustion. And so that piston goes all the way down to the bottom of the cylinder now to its lowermost point, with of course all of these drag points that the oil's creating. And as the piston lowered, even though it was only on the power stroke and not an induction stroke, of course we're still going to get some of that oil seeping past the piston ring and then entering the top of the piston again. Okay, so now the piston's coming back up, and we've still got that drag there because we've still got that oil between the piston and the cylinder. And on top of that, slowing it even further, we've also got that oil on top of the piston there, and it's trying to push into that, and it's slowing the piston down. And of course, as the piston comes up, it's pushing all of those exhaust fumes out the exhaust valve there and out of the exhaust. And of course, as we've mentioned, it's going to be thick blue or thick black smoke because of the incomplete combustion of that oil on the last power stroke. And at the same time, this oil that's actually seeped past the piston on this stroke also starts to get forced out of that exhaust valve there and through the exhaust ultimately as the piston travels up further. Again, this diagram is just to emphasise a point. I've tilted this engine to an extreme here just to explain things. And because of the position it's in reality this engine most probably wouldn't run at all. And one thing I haven't yet mentioned, but I will do now, is that if we do tilt the engines like this, the oil here can cause component damage. And to explain that, we'll revert back to the engine as the piston's rising on the compression stroke. And so as the piston's rising and the oil seeps past the piston there, what can sometimes happen is more oil than we'd expect ends up at the top of the piston here, so it would look something more like this. And because we've got that extra oil there, when the piston rises further into the compression stroke, it actually hits all of that oil. And as we know, oil is incompressible, and because the piston's moving quite fast, it hits that oil, but it stops dead and doesn't go any further. Remember, the oil can't be forced out anywhere to give relief from this pressure because we've got both valves closed because we're on the compression stroke. Now, because before all of this we had a lot of drag with this piston and incomplete combustion, meaning it wasn't moving as fast as it should be, this piston might likely come up and hit this oil and just stop the engine without any further damage. But if the piston's moving much quicker wherever possible and then hits this wall of oil here, then it's going to create some damage somewhere, some physical trauma, and that's normally in the conrod here. Because that piston wants to come up so fast and it hits that wall of oil so hard that the conrod can sometimes shear. And when this does happen, where the piston stopped by the oil like this, we call it hydraulic locking. And so in this instance then, we'd say that this piston is hydraulically locked, and I have seen this happen a few times where customers have bought engines into us and we've took a look and we can see that everything that's occurred that I've explained, and we've got damage there to the conrod. Sometimes the conrods do shear like this, and sometimes there is some less severe damage there. And in other cases, as I've said, there's no damage, the engine has just locked up. But the damage that occurs generally affects the conrods or the end caps here, and it's not necessarily in this exact place, I'm just making a point here. There are other areas that can be affected, like the flywheel here. Sometimes the key that locks the flywheel onto the shaft there in a certain place can shear and allow the flywheel to turn unnaturally in an unnatural position. One important thing I haven't mentioned yet all the way through this, and another reason we can't use a 4-stroke engine on its side like this, is the carburetor. Of course, this is a side view shown diagrammatically, and underneath here we've got the float chamber, which is basically a fuel reservoir for the carburetor. And this is another very important reason we can't turn the engine onto its side. And so to better explain my point on this, I can take this carburetor now and put it in situ onto the engine. And so it'd look something like this. Again, this is just a drawing to explain my point. Things won't be exact to scale, etc. But this is where it would be, something like this. Basically attached to the side of the inlet manifold. And so now if we tip this engine onto its side, we know that the oil won't be here, it'll be down here. And of course it'll be a similar situation inside the carburetor. The fuel won't sit at the bottom of the float chamber like this. It will of course sit like this because of the gravity. And in doing so now, that fuel can start to seep in through the main jet there and start to drip down into the inlet manifold of the engine. And as it continues to flood the inlet manifold, it seeps past the inlet valve depending what position the inlet valve's in. And let's say the inlet valve is nice and tight there. Let's say this engine was stopped on like a power stroke, let's say, so the valve is absolutely airtight and fluid tight, then the fuel would congregate here. It doesn't mean that this wouldn't cause problems, because indeed it would, because when we turn the engine onto its normal position again and try and start it, we'd get an extra flood of fuel that we don't need inside the cylinder there, and there'd be running problems. In fact, it would flood the engine. Of course, the valve could be in this position, but it's more likely to be in a position that will allow this fuel through. And when it does go through, it starts to congregate in the cylinder here. Remember, this engine isn't yet running, it's just been left on its side in its stopped position. But what we tend to find here, as with the oil, when it seeps past the piston rings when the engine's running and then it goes to the top of the piston, we get the same problem here with the fuel. But we don't have to start the engine for this to happen. The fuel, because the fuel is so light, it's not as thick and viscous as oil is, it seeps past the piston rings on its own. And in doing so, it starts to mix with the engine oil there, reducing the quality, obviously, of that engine oil, the ability of that engine oil to lubricate, because it's thinning the oil down, and also it's increasing the fluid mass inside the crankcase there, inside the reservoir. Now, of course, I'm going slightly to an extreme here just to explain my point, but this is the kind of thing that does actually happen in this situation. Sometimes, of course, depending on the position that the engine's in or other conditions of the carburetor, it sometimes won't be anywhere near as bad as this. I just wanted to get this point across in this way. Okay, so that's why a 4-stroke engine can't work on its side. So let's have a look now why a 2-stroke engine can. And when we look into it, obviously we know that the 4-stroke engine here has the oil, and so that's why it can't there. But if we take a look at the 2-stroke, we haven't got any of that oil inside the crankcase here. As we know, we mix the 2-stroke engine's lubricating oil with the fuel. Either that or it's injected in a little later as it goes into the engine. But nevertheless, as the engine uses the fuel, it also draws all that lubrication in, and it lubricates all the parts of the engine as it uses the fuel. As you can see, in some places I've shown that there's no air and fuel in the crankcase, but when the engine's running, they always will be some. I've only shown it flowing like this so that I can show the actual flow of the air and fuel through the engine. But the moral of the story is there's no oil down here in the crankcase like there is in a 4-stroke, and so we can use this engine in any position like this. And that includes being able to run just as efficiently upside down. And so this relates to how the engine can do this then, but what about the carburetor? Let's take a look at that. Well, a little earlier on we took a look at the 4-stroke carburetor and we saw that because of the fuel inside the float chamber there, we can't tip this actual carburetor onto its side because the fuel spills through into the main jet there and comes out in the induction area right down into the engine and causes those problems we mentioned. And so taking a look at the carburetor in its normal position then, we see that it needs to be in this position in order for it to function correctly. We know that because we need a supply of fuel fed by gravity to this particular type. And it's that gravity feed, of course, which fills the bottom of the float chamber here with all of that fuel ready to be used by the carburetor. And that, of course, means that we have to have a fuel tank that's positioned higher than the carburetor in order for it to feed the carb. But as we'll see, the two-stroke carburetor is very much different. There is a storage reservoir here in the carburetor in order for there to be fuel available for the jet, but this fuel down here, it's more containable. It doesn't seep out of this area as does with the four-stroke. And that's because in order to allow any fuel out of here, there has to be more fuel allowed to flood in, or some air or something to take its place. Otherwise, there would build up like a little vacuum in here, not allowing any fuel out. And that's regardless of whatever position this carburetor's in, even if it's totally upside down like this, and I'll explain why a little more. For now, let's just flip it back over where it was. There we go. And just to explain things a little better, let's revert back to our four-stroke carburetor again. And as we know, down here in the float chamber, that reservoir, we've got the fuel. And above the fuel on the four-stroke, we've got air in there. And we need this normal amount of air in there for two main reasons. To explain the first reason, let's imagine this carburetor has never had any use, so it's totally empty inside there, no fuel is in there whatsoever. And of course, because there's no fuel in there, so no fluid for the float to float on, the float would be down at the back under its own weight, as a result of it pivoting at the front here. So this is how the carburetor would be if it was brand new and it had never had any fuel in it and the engine had never been started, or if the carburetor had been cleaned out and put away for winter or something like that. And so with the float down and the needle valve open there, adding fuel in now means that the fuel will flow right past the needle valve and into the bottom of the float chamber. And when the fuel flows in, of course it lifts the float, but what I want to emphasise here is, as the fuel does come in, it occupies space inside the float chamber. And the reality is that the more fuel that comes into the float chamber, the more space it will need to occupy. And so above the fuel here, there is the air I was talking about earlier. And as the fuel flows in, this air has to move somewhere, otherwise the fuel wouldn't be able to flow into the float chamber. And what happens is that this air escapes out of the float chamber by a special tube here, like a ventilation tube. Now these things vary in shape and size depending on the type of carburetor, but they'd be something like this. So as the fuel rises, the air above the fuel then will escape out of this tube and out of the float chamber. And as long as the carburetor is in its correct upright position like this, then no fuel can escape down this breather tube here, because the level of fuel only comes to this level. It will never come to the top there. And that's because, of course, when the fuel gets to a certain height with the float, it lifts up and then shuts off that needle valve there, stopping any more fuel coming through. And so let's take another look at this unused carburetor, where in this scenario this air here can't escape when the fuel comes in. Let's see what goes on then. Well, it would most likely start to try and come into the float chamber there, but the trouble is now, as the fuel flows in, it tries to push out that air above it, and it can't do so well. It might get to a certain level like this, but as it gets further and further up, what will happen is it'll start to try and push against that air. And of course it won't be in high enough concentration or high enough pressure in order to compress that air, of course. And so as that fuel continues to flood in then, what little air pressure there is in here builds up slightly enough so that it pushes up on the fuel there, stopping it from actually entering the float chamber. Just for illustration purposes, I've shown the fuel being this high in here because it will rise to the bottom of the main jet. Because remember, the bottom of the main jet there will allow air out, so it will allow that expansion of fuel. But once the fuel reaches the bottom of the main jet, no more air can get out because the fuel's now blocking the bottom of the hollow tube, preventing it. And so, of course, in a nutshell, the problem of all of this, we can't get enough fuel, or the right amount of fuel, in the bottom of the float chamber here. And with this, as the engine tried to run, it wouldn't be able to efficiently take the amount of fuel it needs, and it wouldn't run so well whatsoever. And so really what we'd encounter here is a fuel starvation issue. And so we can see now why this little simple but effective breather system here is vital for the carburetor. But let's just have a look at another scenario now. Let's imagine we can get enough fuel inside the float chamber there. So even if we could get enough fuel down here, when we start the engine, because the fuel's starting to leave the float chamber through the main jet and then into the inlet of the carburetor there, where it's drawn out and mixed with the air for the engine usage, what now happens is that because that fuel leaves the float chamber there and the engine is quite demanding of its usage, it leaves that float chamber quite rapidly. And that of course means that periodically we've got a smaller amount of fuel here at the bottom. And although this fuel is being constantly replaced because we've got the float hanging down at the back now, meaning that the needle there is open, allowing the fuel in, so it's allowing fuel in as it's being used. In certain situations where the engine's even more demanding for fuel, such as when we're revving the engine to its full maximum revs, or if we're using the choke, using more fuel out of there, then what we're going to get is a sudden surge of fuel out, just slightly more than we can get fuel in. Now this may only be for a very split second, so we'll always have fuel in there to use, but when it does happen, a slight vacuum would appear here in the air. And as we've already gone through, that's because of this fuel leaving the float chamber. And when it does leave the float chamber here, in order for a vacuum not to occur, we need to replace the fuel being lost with more fuel or air above it. But as I've just mentioned, as we do lose fuel there out of the float chamber, more fuel does come in. It's when we get that sudden surges where the fuel's used in high amounts just for that moment that we get this vacuum problem. In those periodic moments, we can't get enough fuel in to replace the fuel lost. So just when the engine needs that maximum amount of fuel the most, there would be less available to the engine there. It's actually pulling back at the fuel to stay in the float chamber. And so with this particular issue then, we can see why again this ventilation tube is vital. Because as soon as a vacuum builds up inside here, what will happen is it will draw in air from the environment into the float chamber, so it'll neutralise that vacuum. That of course means that the fuel can now flow freely up the main jet and out into the inlet of the carburetor to supply the right amount of fuel for the engine needs. So in a nutshell, what I'm trying to emphasise here is that this type of carburetor is designed to run in this position and is entirely reliable on gravity. And when I say that, I mean from the fuel coming from the fuel tank here under its own weight, so under 1 atmosphere, so 14.7 pounds per square inch, under gravity, coming down into the carburetor here and lying at the bottom here, waiting for it to be used in the engine. Of course, when the engine draws that up, it's a different matter. But solely to get that fuel to where we need it, it all relies on gravity. And also we've got the float here that goes up and down like this in order to regulate the fuel coming in, also relies on gravity. And so we can now see from what we've looked into that if this carburetor wasn't firmly fixed into this position, relying on gravity, because that's what it's designed to do, then the mechanisms involved in there simply would not work the way they should do. And therefore the prospect of using this carburetor in any other position than this is near non-existent. So in contrast then, the two-stroke carburetor is very much different. And one main difference we'll notice with the two-stroke carburetor, and what's characteristic of these small two-stroke engines with these carburetors on, is that we've got a fuel pump here inside the carburetor. So this carburetor doesn't actually have to rely on gravity in order to feed it the fuel. Instead, the fuel pump draws in the fuel into it. And so each time the fuel pump rises, it creates a vacuum and draws in fuel from the right hand side here of the image. And then when the fuel actually occupies underneath the fuel pump there, when the fuel pump starts to lower, it actually pushes fuel out on the left hand side there of the image and pushes it right round the carburetor down here towards the little valve here, the needle valve. And the operation of this pump now means that the fuel inside this carburetor is under pressure. Unlike the four-stroke carburetor, which relied only on gravity to get that fuel through, this carburetor pumps its own fuel through, and so of course there's going to be some pressure inside the carburetor there as a result of it. And we'll soon see that this is exactly what we need in order to use this carburetor in any position. So that fuel has come down to this point here, down to the needle valve here under pressure. But as the diagram shows here, it can't get past the needle valve because the needle valve is closed. But in reality it actually could, because if we've got the fuel pump working there inside the carburetor, then that suggests that the engine's moving, so we're cranking the engine to try and start it. And if we're trying to start the engine, of course we'd have air here coming through the inlet area of the carburetor. And it's that air that creates a vacuum, as I've shown in my other videos, drawing out of the main jet there. And when that vacuum draws out of the main jet, it pulls this diaphragm down. This is the metering diaphragm. And as it does so, the metering diaphragm physically pushes the back of the metering lever there upwards. And because it's pivoted in the middle, it pushes the front downwards. And down with it comes the needle valve. And that now makes an open channel for the pressurized fuel to flood into the metering area here. And when it reaches the main jet, it can then be drawn out of the main jet there by that vacuum. And so now with this vacuum pressure pulling out the fuel and the pumping pressure of that fuel pump at the top pumping the fuel round to this area, we've got a constant supply of fuel there in order for the engine to run correctly. And it can provide that fuel regardless of the position that the carburetor's in, whether it be on the side like this or upside down, any position whatsoever. The carburetor will continue to function normally and provide the right and adequate amount of fuel to the engine for engine usage, and it's designed this way purposely, and we can see now why. It's because independent of its orientation we can always get fuel up here into the metering area ready for the main jet to use, and that's because of the fuel pump down here that's always pumping fuel under pressure, drawing it in from the fuel tank and then pumping it round to the rest of the carburetor, ensuring that the whole carburetor gets all of the fuel it needs. And one last component I want to talk about on this topic, and something else that allows this two-stroke engine to work upside down, is the fuel tank. And as we can see on this simplified drawing, we've got the fuel here as red in the fuel tank, and we've got this fuel pipe here that goes and feeds the carburetor. And normally by the time the fuel gets into this fuel pipe here, it's normally been filtered, and so we normally have a fuel filter somewhere like here. However, having a fuel filter stuck to the side of the tank here isn't something we usually see. Instead, what we normally see, and what's characteristic of these small two-stroke engines like this, is that we have the filter which can reach right across the other side of the fuel tank. And it can do this because it's connected to an internal fuel pipe there, which is connected to the main pipe that feeds the carburetor. So, because of this pipe then, fuel can be picked up and used inside the carburetor regardless of which orientation this fuel tank is in. So let's take a look at it on its side. If we look there, we can see that all the fuel has there dropped to the bottom. But because we've got this pipe here, allowing this fuel filter to drop into that fuel, it can still suck fuel out for carburetor usage in this position. And so let's have a look what happens now if we turn this fuel tank totally upside down. Of course the fuel drops to the bottom, as it should do, and what we've got again is we've got the fuel filter that's inside the fuel again, and it's connected by the pipe, so it's still sucking up the fuel and supplying it out to the carburetor again. And lastly, let's take a look at what happens when the fuel tank is tilted this way. We can see there that the fuel has followed its usual path with gravity and it's gone to the bottom area of the tank, and what we can see there with the fuel pipe is that it's sort of bowed over in an N shape, and what's happened is now as a result of that the fuel filter is where it should be, at the bottom of that fuel as a result, because the fuel filter is moving under its own weight, and that's what's allowing this to happen. And of course at that we've got fuel being able to be drawn out of the fuel tank no problem whatsoever and out to the carburetor again in a good feed. And I hope that goes a long way to explaining why and how the good old two-stroke can run and function normally in any orientation. Thank you so much for watching this video, and please do like and subscribe if you've benefited from it, and please do share if you think you know somebody who might benefit from it. And I'll be back soon. Thank you for watching.